All right, today will be a review lecture, and I'm starting kind of from the beginning of the semester, but I'm not going in depth or in detail with a lot of that because it should be stuff that you kind of already know how to do. We've been using it all semester, so we'll start from there and end with what we covered on Tuesday. Course evaluations are due tomorrow, so please fill those out if you haven't already for all of your classes. And our final is 1 week from today. Please note the time is 12:45 to 2:45. It's not at 2 o'clock, right? So make sure that you come, you're on time, prepared, and have everything ready. We're going to talk about that first. Yes?
Is that in this room?
Yes. Okay, so just to re-emphasize, it's so important for you to approach every problem cautiously and systematically and really try to do your best to solve it in a way that I can understand your flow and methodology. So even if you do part of it wrong, I can give you credit. I can see where you were going. If there's something you don't know, write down, I don't know how to do this part of it, but if I did, I would do this afterwards. Okay, all of that will help me know that you understand how the problem works, that you're just stuck at one point, okay, because that happens. So following the problem-solving techniques, hopefully you've been doing it all semester on your homework. Some of you have, some of you haven't. Be reasonable and careful and make sure that you read everything twice so that you don't miss something. I mean, every time on the exams, there's somebody who solved for the wrong thing because they misread the problem statement, so that's pretty important. All right, so the exam itself, I have made an executive decision that you will be allowed to use your textbook on the exam. Is there anybody who doesn't actually have a physical copy of the textbook?
PDF.
Your PDF copies?
Yeah.
I do that too.
I got one from the library because I was waiting for mine to come in.
Okay.
I just haven't
I'll
returned
borrow one of his.
Okay, so who else needs one?
Another one today.
Okay, 3 textbooks. I have a couple of extra ones. So some of them are older editions, but it's the same information. One of the main reasons is just that there are so many equations we used all throughout the semester. And then on the final exam, there's going to be a lot of different tables you'll have to reference. And I don't want to have to print a packet that's like 16 pages long for every student. Having said that, just because you have your textbook on the exam doesn't mean you don't have to study before the exam. Because if you don't know where to find the information in the textbook, you don't know how to use the tables, you don't know how to, if you're relying upon Professor Waite to give you the correct tables for your problem, that's not going to happen, right? So you have to really know and understand how to use the book, where to find things. So I would recommend using your book as a study tool and flagging certain problems or areas. At the end of each chapter, right before you go into the homework problems, there's a nice summary page, which would be good to identify and flag those in each of your books. So you can have your textbook plus 2 pages of notes. And those 2 pages have to be 8.5 by 11 inches. Okay, just to clarify that. Calculators, but no phones for calculators. And your writing utensil needs to be a pencil. You cannot do the exam in pen, because it will make me mad. Okay, so it's comprehensive as was already discussed, and there will be several different types of problems. All of you have taken it in my exams previously. There's always some sort of little short answer problems, definitions, multiple choice, true or false questions. There will be at least two kind of workout problems. And I think one of them is going to be like a power plant, and then one of them is going to be a combustion problem.
Will those be like a megalodon?
Yes, and we're going to look at a megalodon today to remind you how much you love them. And there's also going to be an essay-style problem on there. So it will be graded on content and clarity. Please use complete sentences and punctuation and all of those good things too. It's not going to be a question you have to write like a full page worth, but it has to be something that you answer a question, you give your opinion, you base it, you support that opinion with facts, and something like that. So, and it will be on renewable energy. So please study up, learn about that, think about it, have an opinion on it, and then there will be a question related to that. That will be kind of an essay problem. And that's subjective. And I'm not going to give you poor score if you disagree or if your opinion is different than mine. But I want you to have some, foundational principles behind why you believe or think or act the way you do. Okay? Right, that's life. We disagree about this all the time, that's fine. As long as we're civil and logical. Okay, any questions on the format of the exam?
Chapter 18, will we have that available to us as well?
You won't have chapter 18 available to you because it's the ebook.
Okay.
But there are some equations that I won't print out of that. So if your 2 pages of notes should be from chapter 18.
Okay.
That's another executive decision that I've just made there. Yeah, so you won't have chapter 18 available. Whatever notes you want to take out of chapter 18, that can go in your 2 pages.
So is that like required now?
Is what required?
Notes be from chapter 18?
No, I mean,
Okay.
no, but if there's a problem on, the photovoltaic panels and you have no idea what the equations are for those, then that's not good. Yes.
2 pages in front, like one
Yeah,
front,
front,
one back, or two sheets?
2 sheets of
Of
paper,
front and
front and back, so it's 4 pages essentially, but 2 sheets, yeah. All right, any other questions on this? It'll be fun. Don't stress out at all. It's gonna be great.
Coming right from.
And I'll bring cookies, so it'll be great.
We got you have weird definitions.
I know, and so this will be a breeze compared to that one, right?
Hopefully.
Other way around.
You guys are gonna go home and just, no, you'll be happy when you're done with that day, because it'll be like the worst day of your life, and then you survived it. And
After the weight
you're a
came
survivor
on.
now, and it's okay. Okay, any other questions on this? And you can feel free to ask questions if you think about them as we go through the review today. And I'll try to point out some of the things that I think are really important for you to know how to do. So pay attention if I say something is really important. All right, so general concepts, this is all stuff from last semester. You should know how to do all of these types of things. So using conversion ratios, definitions that are kind of basic to thermodynamics, like what is first law, second law, third law, what is a system, what is a process, what's the state postulate, things like that. How to set up a system, difference between a closed and open system, all of those things. And then, any common assumptions or simplifications that we have made throughout the 2 semesters, like is it an ideal gas, or is it adiabatic, or, is it constant temperature? So those types of assumptions, I will assume that you know how to make them for any kind of given problem based on the problem statement. And then you should be able to recognize and know the difference between heat pumps, refrigerators, and heat engines. So just, this slide has been in lecture several times, but just the difference between the 3, because that's fundamental to understanding the problem statement for whatever mystery megalodon problem I give to you. Could be a refrigerator, could be a heat pump, could be a heat engine. How do you know the difference between the 3, and how would you know? So knowing that, being able to identify and then apply the appropriate equations is pretty important. All right, so chapters 8, 9, 10, and 11. These are kind of the main bullet points from each of those chapters. So chapter 8 was all about exergy. I'm not going to give you an exergy problem on the exam. Just, you can say hallelujah right there. But I may ask you to calculate a thermal efficiency. Okay, but I won't say like find the exergy destruction of all of these steps and phases of this huge megalodon problem. That's not going to happen. But you should know what exergy is, and you should know how to calculate a thermal efficiency. Chapter 9 was IC engines. You just need to know some basic information about that. So what is the difference between spark ignition and gas, or compression ignition, gas versus diesel, auto versus diesel, and then what are the air standard assumptions that may come up. And then how it is different, and this applies not only to IC engines but other problems as well, the difference between assuming constant specific heats and assuming variable specific heats. Because that we learned about that in more detail for ideal gases in Chapter 9, and we've used it in other places since. So what does that mean? What is the difference between assuming variable specific heats or assuming constant specific heats? And I'll just throw that out there right now. What is the difference? How do you analyze those in those two different ways? Like if I say assume constant specific heat, what do you do? Like if you wanted to calculate enthalpy.
Use the tabulated, not the variable ones, I can't think what they're called right now. Just the single value. I can't remember what it's called.
Yeah, so it's like C sub P delta T, right? So if we assume the specific heat is constant, you can calculate internal energy, enthalpy, and entropy using the C sub P values and the equations that are associated with those. If we assume that the specific heats are variable, what do you need to use?
Tables.
The tables. Okay, so that's the major difference between the two, and although that's a concept from Chapter 9, we've seen it again. Chapter 10 and Chapter 11 are kind of similar, except for Chapter 10 is all about heat engines, and Chapter 11 is all about heat pumps and refrigerators. So from Chapter 10 and 11 is where the big megalodon problem is going to come, as we like to say. But we're going to do just a little example of that again today, where we kind of look through and say, okay, we're not going to solve this whole problem, but we're going to start with this system, and we're going to say, okay, what do we know? What do we need to know? How do we find all of the states of this? So this is something that has 12 states. By reading the problem statement and using some of the information that they have given to us in the outset, so they haven't outlined or dictated all the pressures in the problem statement, but they said see the table. And so the table has the pressures of states 1 through 8. How do we find the pressures at 9, 10, 11, and 12? And these are closed feed water heaters, which means that the fluids aren't mixing. So like this just goes straight through, and this goes straight through with the exchange heat.
So pressures 9 and 6 would be equal?
Okay, yeah, so pressure 9 is going to be equal to pressure 6, so it's 1400.
And 7, 10, and 11 should all be equal to, right?
7, well, why 10? Oh yeah, 7, 10, and 11. Yeah. Does everybody see that?
Will these solutions be posted online or not?
No. Write it down.
I have a question.
Yes.
How's it flowing? Like, so from like out of the boiler into the turbine.
Uh-huh. So then it's separated into 3 separate streams.
So
this stream goes through the condenser and then into the pump.
okay.
Then it goes into this feed water heater.
So, but does 7 go to 11?
Just wait, I'm going to explain it all.
Oh.
So we go through this first feed water heater, we go through the second feed water heater, and then back up to the boiler and go around again. Okay, that's if we follow that section of the turbine. If we follow from 7 goes through, it exchanges heat with the stream from 2 to 3, then it goes through the steam trap, and it comes back up. The liquid goes into the condenser to be condensed, and then some of it will come back out at 1.
So it doesn't go from 12 to 8 like back into the turbine?
No,
Okay.
that would be a really bad thing if that happened. Okay, and then from 6, it goes through this, exchanges heat, and then goes into this feed water heater where it combines with 3. Okay, so we've got the pressures now. What about the pressure at state 12? What is that?
It means same as 11?
It won't be the same as 11, because this is, the steam trap acts like a throttling device, so the pressure will decrease from 11 to 12.
If it's a throttle valve, then 8 and 11 is the same as 12, right?
Ooh, yes, good point. So 11 is equal to, oops. Okay, go back to the pressure, how do we know what the pressure is at state 12?
Condenser pressure.
Yeah, it would have to be the same as the condenser pressure. What's the condenser pressure? 20 kilopascals. Okay, so you should be able to look at these problems and think, okay, what's going on here? That looks good. All right. So let's start thinking about enthalpies. We have the enthalpy at state 5. We looked that up because we know the pressure and the temperature that was given. So we can look up the enthalpy, we can look up the entropy. Assuming it's an isentropic turbine, what do we know, or what does that tell us about some of the other states? So we know state 5. What do we know about any other states?
The entropy is the same, the what's coming out.
Okay, so at
6,
6 or 7 or 8 or what?
All 3.
6, 7, 8.
All of them. 6, 7, and 8 are going to have the same entropy. 7.512, 7.512. So then now we know a pressure and we know an entropy, and we can find the rest of those enthalpies from the table. And these all happen to be superheated. Okay, so we know that H12 is equal to H11. Are there any other things we know like that? Like, let's start at state 1. What do we know about state 1 coming out of the condenser?
Same entropy as 2.
We know it's 8.
Yeah, the entropy will be equal. What else? What do we know about state 1? What's always the case coming out of a condenser?
Liquid.
It's a saturated liquid. Okay, so it's going to be Tsat, and our enthalpy is going to be H sub F, so it'll be 251.42. So it's H sub F. So then we can look up our entropy is 0.8320, 0.8320. All right, what other states can we find? I guess we should look at the problem statement. Assume the enthalpies at the feed water exits H3 equals H11 and H4 equals H9. That's good information. So this is going to be equal to H9. This is going to be equal to H11. We don't know 9 and 11 yet. How do we find those?
You said this for the open feed water heater?
Say that again?
You said it was for the feed water heater, right? H9 and H11.
H9. No, H9 equals H4 and H3 equals H11.
H9 and H10 are the same.
Okay, yeah, so H9 and H10, we have another throttling device, so H10 is also going to be equal to H9. Okay, what about state 2? Can we find anything about state 2?
We can find the enthalpy based on the pressure and the
Okay, so from 1 to 2 is pump work, right? So the work of a pump is equal to V times P 2 minus P1, right? Which is equal to H2 minus H1. So H2 is equal to V times P2 minus P1 plus H1. Okay, so we can do that. We can look up our specific volume. It's V sub F at state 1. And then when we calculate this, we find it's 256.48. Okay, so some other things that we can assume is that state 9 state 11 are saturated liquids. That they exchange all of their heat with this feed water so that they come out of there as a saturated liquid,
So anytime you come out of feed water, it's a saturated liquid,
generally.
generally.
But 3 and 4 actually end up being slightly compressed liquids in this problem. So state 9, state 11 is liquid coming out because we want our feed water heater to exchange all of the heat from the steam with the pump water. So at state 9, if our pressure is 1400 and our quality is 0, then our enthalpy is 829.96, and that's the same at state 10. State 11 is 535.35, same at state 12. And then we also know states 3 and 4. So state 3 is 535.35, and state 4 is 829.96. Okay, so once we know all of our enthalpies and all of our pressures, we can easily look up all of our entropies as well. So it's just a matter of reading the problem statement carefully, finding the information that you know, plugging and chugging through the table. So if you have a pump, you can use this equation. If something's isentropic, then you can assume that the entropies are the same. If you have a feed water heater, maybe you need to do a mass balance on that feed water heater to figure out the rest of the mass flow rates. If it's a constant enthalpy device, then the enthalpy stays the same from one state to another. So you have to look for all of those clues within your problem statement. And then if we were to look at this on a TS diagram, how many lines of pressure would we see? How many different pressures do we have?
12.
12 different pressures?
No.
Four. Yeah, there's 4 different pressures. So we have 5 megapascals, 1.4 megapascals, 245 kilopascals, and 20 kilopascals. So if we were to draw our points, if it's isentropic, it goes from this state 5 to 6 to 7 to 8. 8's kind of like maybe on the line, maybe under the line. And then we know that states 1 and 11 and 9 are saturated liquids, and 9 is here. No, 9 is 1400. Here. Okay, we know that from state 1 to 2 is isentropic. And then we have all this going through here. That states 2, 3, and 4 are also at 5 megapascals. This is 5,000, 1,400, 250, and 20. So they're also on that line. State 4, state 3, and then from state 9 to state 10 is a constant enthalpy process, and state 11 to state 12 is a constant enthalpy process as well. And constant enthalpy just looks like a diagonal line on the TS diagram. I think that's all our states. All right. So again, review those types of problems. We've done so many examples of them throughout the semester, so look at them, review them, make sure you understand how to find in many different scenarios, right? So maybe you're given the inlet conditions on the turbine, how do you find the outlet? Maybe you're given the outlet conditions, how do you find the inlet? If you have pumps, if you have throttling devices, whatever whatever things you have available to you as tools to analyze and look at them, make sure that you understand how it works and how it's different. Okay, so chapter 12 was when we were looking at all those partial derivatives and Maxwell relations and the property relations for the real and ideal gases, and we were using the generalized departure charts. I'm not going to give you a problem where you have to use the generalized departure charts on the exam. But you may be asked to use some of these property relations, like you should know how Maxwell relations work, so refer back to the old exam for examples of types of things I might ask you on that. And then chapter 13 was all about figuring out how to analyze mass and mole fractions of combinations of substances, and in that case we were looking at gas mixtures for that. So the Maxwell relations to review, these should be familiar, that they are based upon the 4 Gibbs equations, and then we come up with these Maxwell relations which allow us to calculate a change in temperature versus volume with a constant entropy and say, okay, that's the same as if we wanted to calculate the change in pressure versus entropy if we hold the volume constant, but it's also a negative. So knowing how to take one of these equations and use it to find the other one, not the derivation of how you get to this point, but let's say I gave you some equation for specific volume that's in terms of temperature and pressure, you would need to know how to take the partial derivative of that and then apply the Maxwell relations in order to find whatever I asked you to find. And we've done examples of that in class and on the exam. We had a problem that was similar. So in, generally finding properties using these equations, so if you look at it in the general form, or if you have, you integrate it from T1 to T2, and then using the departure charts, I'm not going to ask you to do that, but that's how those equations work. And then the general form for internal energy, the general form for entropy, and then again, we're not going to do the approximated form of the departure charts, because there's so little time for me to torture you. I have to really pick and choose what I want to use. Okay, chapter 14, or chapter 13. Oh, it was there. Okay. I didn't talk about that because we're doing it in other ways. Okay, chapter 14, specific and relative humidity, so knowing the difference between the two, how to calculate them using these equations. If you need to calculate how much water vapor is in something, so pay very special attention to this, to the homework problem that we did, to the example that we did in class of how to calculate how much water vapor is in a mixture of something, say for example in a combustion process, that's important that you know how to do that. So that hails back to chapter 14. And then we talked about finding the enthalpy of that mixture of air. So atmospheric air is both dry air plus some water vapor, so knowing how to calculate or find the enthalpies for that mixture. Simple definitions like what is the dew point, what does it mean, how do I find it on the diagram. The adiabatic saturation process was a way for us to determine an unknown specific humidity. We can also do the same thing using dry bulb and wet bulb temperatures. So understanding and knowing how to use dry bulb and wet bulb temperatures in these equations to calculate humidity. So we did that as an experiment in class. We've also done homework problems and example problems in class about that. And then using the psychrometric chart, this may be one that I end up printing and including in the exam because I will probably have you draw a process on the psychrometric chart. We've done examples of that, and there are some that we'll look at in just a minute with heating, cooling, humidifying, etc. I want you to be able to pinpoint 2 points on the chart, but then also figure out how you get between the 2 points, because it's not just going to be a straight line. Sometimes you heat the air first, remove some of the humidity, cool it back down. You should understand what each of those processes represents on this chart. So if we look at the lines and what they mean, what they represent, that we have constant velocity, constant specific volume lines, enthalpy, wet bulb temperature, dry bulb temperature, humidity. the saturation line, and then constant relative humidity are lines that go through like that. So knowing how to find those lines, what they mean, how to identify points given two independent variables on the psychrometric chart, and then as we go and look at problems, what does it mean to dehumidify or humidify, okay? And what is the difference between increasing relative humidity or increasing specific humidity? How do I do one versus the other, right? So what's the difference between relative humidity and specific humidity? Or first, what is specific humidity?
So, mass ratio of kilograms to air to kilograms of water is still around.
It's the amount of water that's in the air. Okay, so what does that mean? What if it's 0? What does that mean?
That's dry.
Okay, then there's no water in the air. Right? And it can go from 0 up into, I guess,
It's raining.
100. Well, it's not relative humidity. It would be like you're not in air anymore, you're just in water. So if you go into a river, this specific humidity would be 100%, 100, I don't know, some number. Okay, so, no, it would be infinite.
Yeah.
It would be infinite, because you'd be dividing by 0. Okay, so that's specific humidity. What's relative humidity?
So, percent of saturation.
It's the amount of moisture in the air versus how much the air can hold. How do you increase specific humidity?
Raise the temperature.
Specific humidity.
By raising the water content.
Okay, you add more water to the air. How do you raise relative humidity?
You can add water, you can cool it.
Yeah, so you either decrease the temperature or you add more moisture to the air. So knowing what those mean physically and how it's represented on the psychrometric chart is very, very, very important. Very important. Okay, so air conditioning processes, we can look at them as like a steady flow engineering system. We can do mass balance for air, mass balance for water, we can do an energy balance. We've done lots of examples of that. So if we look on the psychrometric chart for simple heating or simple cooling, heating just means increasing dry bulb temperature, cooling means decreasing the dry bulb temperature. If we're heating or cooling and we're changing the humidity as well, we need to know how that looks. So if we first heat the air and then we add moisture to it, or if we cool the air and by so doing we reach saturation and we have to remove moisture from the air. So knowing how that works and what it looks like on the chart is important. And then evaporative cooling, which is cooling effect that is achieved by evaporating water from a substance or surface or within the air. And then knowing that that's what evaporative cooling looks like, that it follows the lines of, approximately the lines of constant wet bulb temperature or constant enthalpy. Okay, which brings us to combustion. And so knowing all those definitions related to combustion, what is a product, what is a reactant, what does ignition temperature mean, and knowing these rules. So the chemical composition of the products and the reactants is not going to be the same because you've gone through some process that changes it. Knowing, you know, some of these facts like that the mass has to balance on either side of the equation and the total number of atoms has to balance, but the total number of moles is not necessarily the same. Okay, that's a good true or false question there, right? Those kind of facts. Oxidation just means that we're combusting the fuel in the presence of oxygen. Usually it's air, and a lot of times we need to calculate the air-fuel ratio. So how much air is required or how much air is used in order to have this combustion process proceed. So knowing what it means when we talk about excess air, deficient air, theoretical air, stoichiometric air, all of those kind of definitions that go along with that. And it wasn't that long ago that we did these kind of problems, so hopefully they're fresh in your mind. I'm going to have you work together in groups, because what I noticed on the homework, one of the things I noticed on the homework is that your balances were not correct. So be very, very careful when you're doing the balance, because if you do it wrong in the initial stages of the problem, everything is wrong after that. And it makes it a lot harder for me to grade, because I don't know if it's wrong because you did it wrong, or if it's wrong because your number in the beginning was wrong. So when you're putting that stuff in, it gets kind of complicated. So work on these together. Maybe take about 10 minutes, work with a partner, group of 3, however you want to do it. And then we'll come back together and look at the answers.
You want our homework?
Yes, I do want. What's that?
We're gonna do these in these, you want our name on them?
And if you're uncomfortable with these balances, you really need to figure out how to do them.
Yeah.
I might teach it. You guys are just you that can.
Wait, what is
Sit
it?
with someone, if you don't know how to do it, and the person sitting next to you doesn't know how to do it, then sit with someone who does.
I got a C in chemistry. Let's go for it. Well, you know there's going to be some nitrogen in here somewhere. Probably some CO2. Oh, yes. So you have the ATHO2. Let's go start. Can I borrow that pencil? I don't have a number 4. This is how I do it. I don't think he likes it.
What gave you that impression, Blake?
I don't know. That's a hunch. O-N. Oh, yeah. You got the answers, me?
0.6, the O2 is 0.6.
This is how I do it. I set it up like Sean. You have, on this side, you have 8 carbon. Over here, you don't know how many. Yeah. Over here, you have 18 hydrogens. Some numbers.
Which do ATH
For the whole, this whole part in the middle just blows my mind.
So you have these long numbers.
like a bigger number outside of it, but I don't know if you need to multiply this into that.
So I was wondering if it would be.
Yeah.
What do you do with the middle part? This part here.
What do you do with it?
Because when we did chemistry, we did like Sean, then you just say like, you have 8 carbons, 18 hydrogens,
Yeah.
then you write down the other side, and then like just start multiplying till it comes out. But I don't know how to do it with this one. So like you say like oxygen has 3.2.
It would be 1.5 times 2 times 8. Or 1.6.
Why is it?
So we get, you get 3.2A theoretical of oxidation.
Yes, if you're looking at single numbers.
Okay. So whenever you take the large number outside here, and you multiply it by the smaller number there. So our large number outside here is 1.6 A theoretical. So think of that as just one value multiplied by 2. So 3.2 A theoretical. Then the nitrogen, you can multiply 3.76 by 1.6 A theoretical, and then multiply that by 2.
Then you balance to the other side.
To the other side.
No. Ignore me. I forgot to include the oxidation.
Now, does the N2 get removed?
Yep.
So 12.03?
It's 1.6 times.
Do you guys like when I have Ryan look over your shoulder?
So
Because both are equally unsafe, so it does not have to be.
Just sitting at the house, how's that?
When you're not scheming,
When
you're not scheming about.
I mean, you can do it, you can do it.
We don't talk about it at all, honestly, like,
Eighth is there's no
Eighth
saying there's a
no, I mean,
X or Y.
sometimes we're like, hey, you know, that kind
It's all
of
sort of
thing,
just
yeah.
balances.
But no, yeah, no, like, I don't say, hey, I'm giving a quiz today, you should give a quiz today too, and make the students really upset. Honestly,
It's raining today too, we should just really cancel the whole
I
thing.
mean, I thought that's what it meant. Is that what it's,
Blake, just take the bullet for all of us, so we don't have to be hated as bad.
Yeah.
you gotta be nice to him, because he's got leprosy.
oh,
He's got
thanks.
He's gonna die soon.
Oh, he's almost killed.
Yeah, I might.
He left his soaked napkin and glass one day upstairs.
I throw it away.
Arm moves on the paper.
I came back to the class, there was a yellow and red napkin sitting in his.
Oh, man.
Like, he's trying to spread leprosy into the rest of Marshall.
We're all gonna have one weird looking wrist. Good old Blake.
And then, Sean.
Yep. That acronym doesn't mean, it's just that the chemicals.
It makes you feel good, that, yeah, makes you feel like you're
I suppose we use one of that. You guys could.
I don't know. Remember the homework we had to,
That's just 1.6 times.
and then you add,
My brain doesn't work that fast.
Do we need to make this any different?
You have to have CO2, H2.
I do that all the time.
you can do the heat loss, there's excess air going in. That's sick.
How do you know how to break that?
Yeah, you did. It's
I
fine.
know, I just remember that from people.
Oh, how do you know? So if it's a complete combustion, then it's not gonna have carbon monoxide. It's gonna have CO2, water, nitrogen. So if it were incomplete combustion, then the equation might say like in this one, like that there's some carbon monoxide, and so it's not. But if we're assuming complete combustion, it's always going to be the difference. One difference would be is if we had also maybe sulfur on the side of the equation, then we would have a sulfur dioxide.
These now derivations.
Yeah, so then you look at, okay, whatever. That's okay because of that 8 here. And then you can find it.
So how do you find AP or?
I felt worse. When you find both sides of
Math has to do.
Like I said, think of it as a, if I could turn that down.
As explained by Patrick.
I understand that, but you need to understand that you just have to do it.
But it's the same variable on both sides, so you can just move one to the other.
So there's no 6.8, 6.8.
3.28 is equal to 8.02, then.
Well, once you figure out.
1.6. Oh, not 0.2. Yeah, so 3.28 theoretical is equal to, it's not just equal to theoretical, it's there. Two times. It's, it'd be
12.5, then you can use that.
Be whatever.
So on this side of the equation, you're always going to have some excess. If this value is not 1, then you're going to have some excess oxygen that comes out of the equation. So then the excess just comes out of 0.6 times a theoretical. Because it consumes the combustion equation as the combustion reaction consumes a theoretical, and then the extra. Yeah, it passes. It doesn't burn.
I got a feeling about it.
Which part? 75.2.
Please don't get that right.
It's all right. I have 160, 22 credit hours.
I didn't see.
First time I've ever seen like Jasmine used to.
I've given up on this one.
They do it in chemistry.
Who's got it? When you find 8,
Chemistry and King's.
We always have 1 kilogram. Always.
So the ATH equals just what this is divided by the amount. Right. And then same for here. The next one is the ATH equals whatever that value is divided by 12.0. So we might be able to like 1 ATH. Yeah, just do your regular balancing.
What I'm confused is once you find that, then once you find the 8, it screws up this and that.
No, it doesn't.
It'll both just do the same.
I think instead of doing Chan, you should do how you were doing.
I don't know how that.
How did you do the homework?
Reached over here.
What's wrong?
Hang out with my buddy,
I know.
have some beer.
That's right, I know.
Yeah.
This is a good exercise because this will be worth a big part of the exam.
You know, you're the fourth teacher to try to teach you how to do this.
And you still haven't learned?
Still, just, yeah.
It's just two sides of an equation with unknowns in it. And you just
this point, it's like a very personal.
So this
It's like a personal slice.
8 for CO2. Then it's 0.68 O2 plus H2O. So for H2O, you can multiply by 9.
No, that's your gas.
Which would then give you 9 oxygens. No,
I mean, they're all gonna turn into hydrogen, they're all gonna turn into water, carbon
So
dioxide,
9 plus 18
Excess.
plus 7.
whatever nice.
I don't think there will be
then you
any efficiency in that one because it's not.
27.
0.02 in here.
On this one, because these have, you still store the CH2, so that's all you have.
This one's
This one's gonna be areas.
Yeah.
Divide by 3.2, so you go to 8.68.
So you know we took first one there. I just hear it. Spend that 6 seconds. Come over here, so multiply it by 1.2. We got tons of stuff, it's not right.
7 divided by 3.2. So 8 plus equals to 8.75.
Not bad, it's not bad.
Well, you're way ahead of us.
Did you already balance the other side?
He said it's.
What did you get for that?
Hey man, it's a long shot.
He did 3.76 over here, which. Right. No, because 3.76. Because we think there should be an 8.
There should be a here. They're supposed to multiply it by 1.6.
Well, no, because there's no excess nitrogen.
There is.
The only reason you have 8 there is because there's excess oxygen. It's not being burned.
Yeah, but look, this is multiplied by oxygen and nitrogen.
I know. But I'm saying once it goes out of the combustion chamber,
There's no nitrogen.
there's no nitrogen, which is excess. I mean, there is, but it's not excess.
Balance, it's not.
Yeah.
But we still have 12.032.
Did you do it like 10?
Over there.
Of nitrogen.
Yeah, well, that's 2.76.
I don't know.
Times by 8.
Or it'd be what this total figure is right here.
Would it just be?
Where is this total figure? 1.6 times 2 times that.
Yeah, that's what we're so that's what
Okay, so we're gonna move on. Keep working on these on your own time, and I'll scan the solution and post it, so you can kind of check and see. The reason I'm scanning the solution is not so you can fill out this paper and have it done, it's so you can figure out how to do it, right? So this is very important. I see that some of you are struggling. This is integral to being able to be successful on the final, okay? That you have to know how to do this. So no pressure, but there's a lot of pressure. Okay. So once we have balanced our combustion equation, then we can look at the enthalpies on both sides. We can do an entropy analysis. We can use it, or we can perform a first law and a second law analysis on these combustion equations so that we can calculate whatever it is that we want to, entropy that's destroyed or generated, or not entropy destroyed, entropy generated or exergy destroyed. So we have a couple of different scenarios. The first that we look at most often is an open system, so we have air coming in, fuel coming in, and then some byproducts coming out. Sometimes, and a couple of the examples in homeworks, we had a closed system where maybe you have oxygen plus something else inside of a closed container, and then when you add heat to it, it ignites or it combusts, that the reaction occurs. So we're not going through the examples of doing this, because we've done a lot of those examples in class and on the homework and things like that, but I want to point out a couple of things that I saw on the homework that I think was problematic. So this enthalpy of formation, you look that up for every reactant and every product. For O2, N2, and several of the other diatomic molecules, that enthalpy of formation is 0. So make sure that you are very systematic and methodical when you're looking these property values up, that you first separate your products from your reactants, but then also look up the enthalpy of formation for each of them and get the correct value. The second part of it is this H minus H naught term. So this H naught term is defined at 25 Celsius or 298 Kelvin. If let's say your reactants are at 298 Kelvin, then this H minus H naught is always going to be 0. If your products are at 298 Kelvin, then the H minus H naught is always going to be 0. Because you'll look up the H value at 298, you'll look up the H value at 298, and it will subtract at the exact same value. Okay, so if something is coming in at 25 Celsius and leaving at 25 Celsius, then all you have to worry about is the enthalpy of formation of the products and the reactants. If it's coming in at 25 Celsius and leaving at a different temperature, then when you're looking at the reactants, this term will be 0. But as you're looking at the products, it's going to be whatever temperature of the product. So you would look up maybe at 1400 Kelvin or whatever it might be, minus the H naught at 298 Kelvin. So be clear about that distinction, that this H minus H naught is applicable. It's always applicable, but it will end up going to 0 if you're at 298 Kelvin. So know what temperature you're at when you're analyzing your products and your reactants, because that's important. And then the same thing goes for any of these other equations. This term here, this R sub U times T, is the temperature of the product or the temperature of the reactants. So again, temperature is important, and use Kelvin when you put that information in. And then when we're looking at the entropy changes, it's a similar idea, and I think a lot of people did this problem by copying in the homework, because there was not a chart that included these y sub I values. So in order to calculate this R sub U natural log of y sub I, you actually have to perform a molar fraction analysis of your products and your reactants so that you can get all those y sub I terms. So go back and review that homework that hardly anybody did. I know you didn't do it, so you need to know how to do it, because this will be on the final. Okay, there's going to be a problem like that we did on the homework, that we did that it will be a combustion problem, so you have to be able to balance the reaction. You have to know which enthalpies to look up and what part of the equation they go into. And you have to know how to calculate these entropy terms. Okay, that's going to be a big chunk of the final. It's going to take you a long time. It's going to be worth a lot of points. And I'm forewarning you, so there's no excuse for you to not know how to do that. All right. Okay, so renewable energy, yes.
What chapter was that from?
15. Yeah, 15. So, carry on. All right, so renewable energy, again, this is from chapter 18, which was the online chapter. Any notes that you want from that, you will need to put onto your 2 sheets of pages of notes, because you won't have access to this in the exam. I'm not going to let you look it up or anything like that. So, knowing how to analyze, let's see, so let's go back to this one. Yeah. So chapter 18, these are the things I want you to focus on. Any of the definitions and nomenclatures that we use. So what is a flat plate collector? What is a trough collector? What is, being able to identify things and to know definitions of things is important. So all of those definitions from chapter 18 you should know. I'm not going to ask you, what's the process of converting ethyl, corn to ethyl alcohol? You're not going to have to know that, but you would have to know, the conversion of corn to ethyl alcohol is an example of what type of renewable energy, Oh, that's biomass, right? Okay, so things like that. So what is biomass? What is geothermal? What is solar? What is wind? What is those sorts of things? But you will need to know how to analyze solar, wind power, and hydropower systems. So there's some equations for those. They won't be any more difficult than what we've seen in class or on the homework. But then the rest of this is mostly conceptual. So the benefits of renewable energy, challenges, this is where an essay question is most likely to come in from that. All right. So solar collectors, knowing, again, these kinds of definitions, I'm not going to ask you to calculate these transmissivity, reflectivity, absorptivity, that's a different class. Flat plate solar collectors, those equations are all important. You may need to analyze or calculate using those. Concentrating solar collectors, again, useful and important equations. Knowing what these things mean, so what is a concentration factor, what does it physically represent, what is optical efficiency, what is, these types of things, what do they mean? Thermal efficiencies, how you would calculate them for a solar power plant or maybe for a solar pond, what's the maximum thermal efficiency that can be achieved. And then these photovoltaics, on the homework we did have some problems where we had to calculate this, let's see, the voltage, the max voltage or something like that. You have to use solver to do it. I'm not going to give you one of those problems, but you may have to use any of these equations. So I would write them down and I would know what J sub J means and J sub S and J sub naught, what are those things. Passive solar applications, so we did some examples where we looked at sun incident solar radiation on sides of buildings, so maybe you'll have to use, if I want you to use that table, I will print it and include it in your exam, but how to calculate how much solar radiation is up on a building, how much heat may be gained, how you can choose the right windows, maybe something like that. For that, yes?
I think there was one question where it said they had double pane windows. Is that the same as like double glaze?
Yes.
Okay.
Double glaze, because, yeah, so glaze is not like a glaze. People who put in windows are called glaziers, or glaziers in French. It comes from the French word. So, yeah, double glaze means double pane.
Okay.
2 sheets of glass with air in between. Yeah, because it kind of seems like, you think of glaze as like glazed donuts, or if there's something you're putting on the window, no, that's the glass itself, double glazed. It's just another way of saying it. It's kind of an old, tiny way of saying it. Okay, wind power potential, being able to, given certain conditions, calculate how much wind power would be available, maybe being able to compare two areas one to another, see which one is better. There may be some sort of an economical problem that comes in with this where I say, it will cost this much to build it, how long would it take to pay it back? I haven't read the exam yet, so, but I do know what I am putting on it. Big fat combustion equation. Okay, so then calculating efficiencies, all that sort of thing, that the efficiencies combine by multiplying. And then with this, maybe just conceptually, what is the best limit? What does it represent? Why is there a limit? Why can't we have 100% efficient wind turbine? Why can't we?
It's not possible.
You can't bring the air to
Yes, we can't because it's not possible. But why is it not possible?
Because you can't bring the air to rest to extract all of its.
On the other side of the blade.
So you can't go from some velocity to 0 velocity. It would be like you're in some kind of a warp, tiny space warp if you were able to do that.
Does a similar law to the Betz limit apply to fluid turbines?
Yes. So hydropower, how to calculate, so knowing, what this means for hydro turbines, stuff like that. Okay. Yeah, so all of that stuff. And then when we talk about renewable energy, so geothermal resources, where can you find them? What do you do with them? Biomass energy, what is it? What are some of the sources? How do you convert it? not necessarily in detail telling me how to convert it, but just kind of generally that it's either a chemical process or a thermochemical process, or it has to do with light. What are some of the products? How are they used to produce energy? And then, talking about municipal solid waste, so like the video we watched, maybe some of your opinions on that. I don't know, I haven't developed that question yet. So, be very focused in your studying. Make sure that you address your weaknesses. So if you can't figure out how to calculate quality, you've never known how to calculate quality, and that always trips you up, you better figure out how to do it, okay? If you can't do the combustion equations, you better figure out how to do it. If you had trouble on homework 11, and you didn't do the homework 11 yourself, then you really better figure out how to do it. So that's my advice. If you have any questions, email me, I'll be around, probably not on campus, but if you needed me to come to campus to meet and talk about things or whatever, then I can set up an appointment or via Skype or however you want to do it. I'm happy to help you. I don't like to just give you a super hard exam and watch you all fail. That feels terrible as a professor to have your students fail. To me, some people may like it, but I'm not sadistic that way.
Everybody's got a hobby.
I want you to do well. What did you say?
I said everybody's gotta have a hobby.
No, that's not mine. Mine is being in nature. I'll bring the rest of the lollipops from Halloween. You don't want to be on lollipops.
Bring blankets.
Don't tell me what to make. I'll bring whatever cookies are left over from the thing I got left.
You would be, because I know you brought it up when we were talking about, how much coal produces. They come in and borrow. He didn't know what.
Yeah, but even still, you would think, okay, our state is so poor. People are working.
So you know when you're going to
The way they run things then, they never change. They got unions and stuff. They still run things on the ground.
Right.